Every moment of your day is shaped by invisible chemical messengers, all right? Be it lights, be it sound, be it chemicals in the air, flavors on your tongue. But how does your body transform these signals into sight, hearing, smell, and taste? Welcome to the world of special senses, the body's most advanced detection system. Your eyes act as biological cameras, bending photons into images your brain can understand. Your ears decode vibrations from air and convert them into music you love, or even alarm that wakes you up, or sounds of people talking, or even as you're listening to me right now. Your tongue performs chemical analysis in real time, detecting sweet, sour, bitter, salty, umami. And your nose, believe it or not, is one of the most powerful survival tools capable of recognizing over 1 trillion scents. Today we are, going to jump deep or dive deep into how these senses work, why they matter, and the incredible science happening behind every blink, every taste, every sound, and every breath. Sensory input is vital to the integrity of the personality and intellectual function. We know this because, when you deprive somebody of the sensory input, it can cause hallucination, all right? And another thing you need to also understand is that some information communicated by sense organs never come to our conscious attention. Take an example. Your blood pressure can go up without you knowing it. Your body will just adjust, correct. Sometimes your body temperature can go up or go down, and your body will correct it. Same thing with muscle tension. So they don't really come to conscious attention, all right? These sense organs, initiate somatic and visceral reflexes that are indispensable to homeostasis and to our survival. We're talking about homeostasis because we are talking about physiology, normal. We're talking about being normal, all right? Physiology is normal function. You see, I blink my eyes, normal function. If I don't have the ability to blink my eyes, it's no longer physiology, it becomes what? Pathology. So pathology is what? Moving from normal towards abnormal. Now, when you're talking about visceral and somatic reflexes, you're talking about body reflexes and organ reflexes. All right. If you don't understand it properly, please go back to my video on neuro. I have neuro 1, neuro 2, neuro 3, and look at it. Please make sure you subscribe to this channel. Make sure you comment. Make sure you put on your notification bell, please, so that you'll be notified of every information. Please. Now, to start with, let us talk about the overview. What are we learning from today's discussion? We are going to employ more than 50 questions to discuss this topic, right? Because the more questions you attempt, the better for you. General properties of sensory receptors. We are going to talk about sensory receptors. Why it's very important? Because that is the hallmark of everything we do in special senses, all right? Now, classification of sensory receptors, the chemical senses, taste and smell, hearing, equilibrium, vision and visual processes, sensory pathways, and integration. These are the major things we are going to discuss in this video. So I want you to pay more than usual attention. I want you to write out the questions I discussed, generate more questions so that you'll be able to understand special senses properly. To begin with, what is sensory receptor? What is sensory receptor? Sensory receptor structures that are specialized to do what? To detect stimulus. Extremely important that you know this. They detect what? Stimulus. Some of them are naked. We call them bare nerve endings. They have bare nerve endings. Some of them are covered, right? Surrounded by other tissues, all right? But the most important thing is that they are specialized to detect what? Stimulus. And that's what we are discussing today. They have special properties. They have special properties. And one of those major properties is transduction. What is transduction? Is conversion of one form of energy to another. One form of energy to another. What energy are we talking about? Specifically for special senses, we are talking about light, heat, touch, sound, and others. And they convert all these energy to nerve signals. That is what? Transduction. Then we have receptor potential. What is receptor potential? Small local electrical changes on the receptor cell brought about by what? A stimulus. So when the stimulus happens, all right, it triggers small electrical changes. That small electrical changes is what we call potential. Where is that potential happening? In the receptor. You need to know this. Now, what does it lead to? That potential will lead to either release of neurotransmitters or what? Or action potential. Very, very important. And that action potential will now generate nerve signals to the CNS. This is a sequence. This is a chain. But if you understand it, good for you. I'm going to give you some questions that will help you to understand this concept properly. As a summary for sensory transduction, we already discussed transduction is conversion of one form of energy to another, all right? And its fundamental purpose is to convert stimulus like light, heat, touch, sound, chemicals into what? Nerve signal. And all sensory receptors output is always what? Electrical. You must remember this. all sensory receptor output is what? Electrical. For example, they ask this question. The output energy of all receptors is a type of dash energy. You see? They give you chemical, mechanical, thermal, electrical, nuclear. It is always what? Electrical. And how about if they ask you this question? The initial effect of a stimulus on a sensory receptor is a local electrical change, specifically called dash. What is that change? I told you initially, that change, that small electrical change on a receptor cell caused by stimulus is known as what? Receptor potential. Receptor what? Potential. Also called what? Generator potential or what? Sensory potential. And what does it lead to? It leads to action potential generation or what? Neurotransmitter release. Talking about sensation, sensation is the detection of a stimulus that results in a receptor potential. Mind you, it results in what? Receptor potential. And when it results in this receptor potential, it initiates neural signaling to the brain for interpretation. So it's more like a subjective awareness of the stimulus, all right? Most sensory signals, they are always what? Delivered to where? The CNS. They're always delivered to what? The CNS. But those ones that are delivered to the CNS, they produce no conscious sensation. Most times, they are filtered out in the brainstem, thus preventing information overload. Some signals do not even require conscious awareness, which I discussed initially. Now, those receptors, they transmit 4 kinds of information. We know them as modality, location, intensity, and duration. Modality, location, intensity, and what? Duration. When you're talking about modality, you're talking about, type of stimulus or sensation it produces, like vision, hearing, taste. When you're talking about location, you're talking about the nerve fibers, all right, that is firing it. That's the receptive field. That's what we mean by location, all right? And when you're talking about intensity, intensity is coded in different ways, which is how the brain can distinguish stimulus intensity, all right? Which fibers are sending signals? How many fibers are doing so? How fast these fibers, how fast are they firing? This is what we call what? Intensity. And when you're talking about duration, how long does the stimulus last? That is duration. How long does the stimulus last? Then it will lead us to discussing phasic receptors and what? Tonic receptors, which I'm going to come to in a minute. So the key components of sensory sensation is 1, stimulus detection by specialized receptor, generation of receptor, that's generator potential, conversion to neural signal, transmission to the CNS, conscious or conscious what? Perception. Now they will ask you a question. What is a sensation? You see a question like that? What is a sensation? They'll give you options like detection of a stimulus resulting in generator potential, detection of stimulus resulting in resting potential, detection of stimulus resulting in receptor potential, detection of a stimulus resulting in conduction potential, detection of a stimulus resulting in transducer potential. My answer is what? Receptor potential. Remember. That's why, I critically mentioned it. Receptor what? Potential. Receptor what? Potential. Now let's talk about classification of sensory receptors by stimulus type. We have chemoreceptors, we have mechanoreceptors, all right? Very, very important that you know this. We have thermoreceptors, we have nociceptors, we have the photoreceptors, and we have proprioceptors. Now, the major classification is chemoreceptor and what? Mechanoreceptor. When you're talking about chemoreceptors, all right, they detect what? Chemical. Chemical. All right. What kind of chemicals? Like CSF, like pH in the CSF. All right. Oh, CSH pH reduced, increased beyond the normal. Initially, the central chemoreceptors we triggered to correct it. Also, we have blood gas levels. We have peripheral chemoreceptors to take care of it. How about test molecules? Test molecules, we have what? The gustatory receptors to take care of it. How about odor or olfactory receptors? Think about it. Odor, olfactory receptors. So all these things are chemoreceptors, rather. Let me tell you, one of the following is not chemoreceptor. They will tell you central chemoreceptor, peripheral, gustatory, olfactory. You know what to choose. Or they give you options as changes in pH, in CSF pH, blood gas level, test molecule, odor molecule. You should be able to know that all these things are what? Chemoreceptors. Now, they ask a question. Now, let me give you a question. Changes in the CSF cerebrospinal fluid pH are detected by dash. Chemoreceptors, you pick it and you go your way. Because they'll give you options like chemoreceptors, thermoreceptors, nociceptors, mechanoreceptors, proprioceptors. No, I'm going to show you what each and every one of them stands. So we discussed chemoreceptors. How about mechanoreceptors? Mechanoreceptors detect what? Mechanical what? Forces. Example of mechanical forces: blood pressure change, pressure, vibration, stretch, sound waves, body position. All these things are under what? Mechanoreceptors. Make sense? See? Blood pressure change, you talk about baroreceptor. Pressure, vibration, stretch, you talk about tactile receptor. Sound wave, you talk about cochlear hair cells. They are also receptors. What body positioning? Proprioceptors. Yes, they're additional. Talk about thermoreceptors that detect heat and change. They have free nerve endings, which is sensitive to temperature. Talk about nociceptors. Nociceptors are what? Pain receptors. You must know that nociceptors are what? Pain receptors. What do? They detect tissue damage and painful stimuli. They have free nerve endings, just like the thermoreceptors. They detect pain, heat, cold. The brain has no nociceptors. You remember that. The brain has what? No nociceptors, so it cannot feel pain, all right? But there's something we call referred pain, like the heart. When somebody's having a heart pain, now you see the person having pain in the problem in the heart, see the person having pain in the hand. That's called what we call referred pain, because the brain is confused. The brain is thinking that, okay, that pain is coming from the skin, all right? That's what we call referred pain. You see some people, they may be having abdominal problem and they already having chest pain. Maybe ulcer, for example, they have chest pain, back pain. That is also called referred pain. These organs feel pain, but they localizing the pain. The brain is localizing the pain for them in a different place, all right? Now, it's different from the brain itself. The brain does not feel any pain. So if I bring out your brain and pierce something inside it, you feel nothing. Why? Because it has no nociceptors. Extremely important that you know this, because then we ask you in question. Now, we have photoreceptors that detect lights, rods and cones in the retina. We have proprioceptors that detect what? Body positioning, movements. Like when police stops you for DUI, what they want to check is what? Your proprioceptor. Now, if they ask you a question, changes in blood pressure are detected by dash in certain mechanoreceptors, chemoreceptors, proprioceptors, nociceptors, thermoreceptors. Put the answer in the comment section below, all right? Thank you. Now, let's talk about sensory adaptation. How do you adapt? How do you adapt? How does your senses adapt to these things? All right. So we have the phasic receptors and we have the tonic receptors. The phasic receptors are the ones that respond quickly and they adapt rapidly. But tonic receptors, they respond slowly and they adapt what? Slowly, but more sustained, more continuous. For example, if I enter this place and I have a very good colon on me, you perceive it quickly. Immediately I entered. That is an example of phasic receptor. But what happened? Give it a couple of seconds. Or before 1 minute, you stop perceiving it, but the smell is still there. Why? Because you adapt quickly to it. So, phasic receptors, fast, they respond quickly to stimuli, onset, then they adapt quickly. Example is what? Olfaction, smell. Now we have what? Tonic receptors. This one's slowly but sustained. Like what? Pain. You see pain? If I prick you here, it's you feel it slowly and it keeps getting bigger until it places out and it's continuing to be sustained, all right? And this has very clinical relevance because it helps to warn the body of anomaly. Oh, that there's a problem, so that the body can what? Respond. Now, what do you need to understand for your exam? Somatosensory pathway. Nociceptors, spinothalamic tract, thalamus, then postcentral gyrus. That is the sequence. Anyway, go anywhere. That's what you need to know. From the nociceptors to the spinothalamic tract, to the thalamus, and also to where? To the postcentral what? Gyrus. That is somatosensory pathway. Extremely important that you know this. So the key points you need to have in your head, the key repeated question in your exams, college exams, NCLEX, is usually about, where they meet, all right? Like most second order somatosensory neurons, where they synapse with what? Third order neurons in the thalamus. You must remember thalamus. Do you understand? In the thalamus. And also you need to know the spinal gating of pain, all right? Very, very important because nociceptors are involved. So what are the things, they will ask you, what are the things involved in the spinal gating of pain? Talk about nociceptors, spinothalamic tract, second order neurons, reticulospinal tract. If you don't understand any of these things, please go back to my video on Neuro 1, Neuro 2, Neuro 3 and understand neuro properly. Answer those questions that I'm asking. You can pause the screen, respond to the question, and continue and know if you're right or wrong. All right? So pain can be modulated at spinal cord level before what? Reaching conscious what? Perception. Now, that doesn't mean that the body does not help. The body actually helps. The body actually produces natural pain relieving compounds. So even if you don't go to get drugs, the body will help you take care of most of those things. So the body has natural analgesics. What are those natural analgesics? We have the endogenous morphine. We have the short-acting peptides. We have the potent opioid peptides. They are going to ask you. The endogenous morphines like the endorphins, the short-acting peptides, the enkephalins, and the potent opioid peptides, that's the dianophins, all right? Extremely important that you know that. All these ones are natural analgesics. Now, the body still produces things that mediate pain, but they are not what? Analgesics. Like what? Like bradykinin. It's actually a pain mediator. It helps to make that pain visible, all right? Bradykinin. Bradykinin is usually released when there's a tissue damage, all right, causing pain and a lot of inflammation, so that the body will be aware that there's a pathology, there's a problem. So then with time, the natural analgesics will start helping you before you even start helping yourself. That's why sometimes you see injuries on your body that you don't even know when it happened. Keep asking, when did I have this kind of cut? Like, you don't know when this cut happened. All right? Extremely important that you understand this. As a recap, organs with nociceptors. Which organs has nociceptors? We have the heart, can experience pain. Like, that's why we usually have sometimes angina or heart attack pains. The kidneys, you have renal colic from stones. The stomach, you can have ulcers, you can have inflammation. The skin, that one is even very expensive. Anywhere pricky on the skin, you're having pain. So it's very, very extensive, all right? Extensive nociceptor distribution. What are the organs without nociceptor? Brain. Some people will be like, oh, but this person has a headache. The headache is not from the brain. It's usually from surrounding structures like the meninges, like the blood vessels, not from the brain itself. So that's what you need to know. Like, the clinical significance is the brain tumors, they don't cause pain until they affect what surrounding structures. Extremely important that you know this. They can ask you a question. What are some of the questions they can ask you? Think about it. They can say, for example, they ask you this question. You can smell the fragrance of your deodorant when you just put it on, but after a while, the smell fades. What explains this phenomenon? It is the basic nature of olfaction. Olfaction, very basic. They can ask you which organ does not have nociceptors. Put the answer in the comments below. All right. When you put the answer, please write the question and put the answer so that I know what your answer. All right. They can ask you pain, heat, cold are detected by what? Tactile disc? No. Tactile corpuscles? No. Lamellar corpuscles? No. End bulbs? No. Free nerve endings? Yes. I mentioned it. Free nerve endings. Extremely important that you know this. What if they ask you which of the following is not an analgesic pain reliever found naturally in the CNS? You should know the analgesics, like the endorphins, the enkephalins, the dianophins, the endogenous opioids. What about bradykinin? Is it a natural analgesic? No. Instead, it is a mediator. It enhances the pain. They can ask you about where do the most second-order somatosensory neurons synapse with the third-order neurons. What is the answer? Put it in the comment section below. All right? When they ask you about spinal gating, look at this question. Which of the following is not involved with spinal gating of pain signals? We have the nociceptors, we have the spinothalamic tract, we have the lower motor neurons, we have the second-order neurons, we have the reticulospinal tract. Think about it. Which one? Put the answer in the comment section below. Okay, let me help you. The answer is lower motor neurons, because upper and lower motor neurons is talking about return. It's talking about motor coming back. But this is what we are talking about, was somatosensory going up. That's why you need to go watch that video, please. We encourage you to go see the video. Somatosensory going up. Now let's talk about the sense of taste. All right, the sense of taste, very important that you know it. Known as gustation. All right, gustation, sense of taste. All right, what is involved? Remember, this is anatomy and physiology. Anatomy is location. Physiology is what? Function. I can also tell you that anatomy is what? Structure. Now, when you're talking about taste, sense of taste, all right, remember we finished olfaction, sense of smell. Now, sense of taste. Talk about the structure. Talk about, both the taste bud structure, the visible structures, and the pores. Also the hairs, all right? All these things are involved in sense of taste. So when you're talking about taste bud structure, you're talking about gustatory cells. These gustatory cells, remember I told you, receptor potential. Something must produce that receptor potential. For sense of smell, it is the gustatory cells that produce what? Receptor potential. They will ask you this question. That's why I put it in highlights, all right? These gustatory cells are the supporting cells that provide what? Structural supports. We also have what? The basal cells, all right? The basal cells that help to replace the supporting cells or the gustatory cells. Now we have the visible structures like the lingua papillae, that's visible bump on the tongue. You see? That is the visible bumps. That's the lingua papillae, all right? It contains the taste buds. So those buds are inside the lingua papillae. Example, the circumvallate, that's the largest, the fungiform, the foliate, the filiform, all these ones are involved. They are involved in the lingua papillae. Now we have the taste pore, all right? That's the opening where, testants contact gustatory cells. That contact area. That's what we call taste pore. Then we have the taste hair. The taste hair are the microvillus of what? The gustatory cell. Extremely important that you know this. What are the basic tastes that you can get? Sweet, sour, salty, bitter, umami. All right? Umami is usually from amino acids, the one we see in chicken. If you taste meat, chicken, cheese, mushroom, all those things, you see, you feel the aspartic acid and glutamic acid. This combines together to produce that umami taste. Extremely important that you know it. Why bitter is usually alkaloids and toxic substances. In Nigeria, they say bitter is very good. Bitter is very good. All right? But what you need to know is that bitter is usually from alkaloids and toxic substances. Salty is usually from sodium. Sour is usually from acids. and sweet is usually from sugar. You need to understand it. Very, very, very important. What you need to know about the olfactory cells, all right, is that they are directly stimulated by odor. Immediately the odor comes, it stimulates them. Where are they located? In the olfactory epithelium of the nasal cavity. They will ask you, all right? And they are usually bipolar. They are usually what? Bipolar. There's something called pheromones. Pheromones are chemical signals between individuals, because human body odors may affect sexual behavior. A person's sweat, vaginal secretions affect other, people's sexual physiology. We call it dormitory effect, all right? So maybe presence of a man or men seems to influence female ovulation. Funny enough, all right? And even ovulating women's vaginal secretions contains what we call what? Pheromones, called what? Copulins. Special pheromones for ovulating women called what? Copulins. This copulins has been shown that, when men perceive it, it increases their testosterone level. So this is about pheromones. Now we have discussed the supporting structures already, like the olfactory glands, which produces mucus. We talked about the supporting cells, which provide structural support, and also the basal cells, which helps in regeneration of olfactory neurons. All right. So if you look at that diagram very well, you see how the sensation comes in, right? Goes to the primary olfactory cortex on yellow. All right. Primary olfactory what? Cortex. Then from there, it starts spreading. From that primary olfactory cortex, it spreads everywhere. It can spread to the amygdala. So I perceive somebody, I say, okay, I know this person. Just from the smell. Why? Because the smell gets to the amygdala. I love this person. Oh, this person. Amygdala. Or it goes to the hippocampus. You can remember that smell just because it went to the hippocampus. Remember, the hippocampus is for short-term memory. Then the hippocampus will now train the cortex. You need to go watch that video on neuro, all right? Neuro 1, neuro 2. Sometimes it goes to the insula. Sometimes it even goes to the, at the end of it, it goes to the orbitofrontal cortex. This is ways it spreads, spreads. Sometimes to the hypothalamus. It can go to the hypothalamus. You know that, right? And when it goes to the hypothalamus will start secreting things. Remember, if you've not watched my hormone video, please go watch that video. Because the hypothalamus produces 8 hormones. 2 goes to the posterior pituitary. 6 goes to the anterior pituitary. Those are the releasing hormones. Then the one that goes to the posterior pituitary, oxytocin and vasopressin. So you need to go watch those videos so that you'll be able to follow. Anatomy is sequence. You just don't watch it and throw it away or learn and throw it away. It's a sequence. You have to keep learning it. You have to tie it together. If you don't tie it together, you will never have proficiency in anatomy, all right? So as a recap, all right, the olfactory bypasses, we already discussed it, all right? The olfactory is the only sense organ that can reach the cerebral cortex without passing through the thalamus. Others pass through the thalamus, just only olfaction, all right? And the sequence is from the olfactory bulb to the olfactory tract, then from the olfactory tract to where? Primary olfactory cortex, known as the temporal cortex, all right? And that's why you can remember smells a lot. So there's powerful memory association with smells, immediate emotional responses, which I mentioned, conscious behavioral influences, rapid smell identification. All these things, right, it's because they move straight up. They bypass the thalamus, right? No time. There are some questions that they can ask you. For example, they can ask in the test board, which cell produces a receptor potential? It is a gustatory cell. I mentioned it initially from the outset of this when we entered the olfaction, all right? Now they may ask you which structure is visible to the naked eye. Know that the lingua papillae is visible to the naked eye. Remember when I did like, you see these bumps? That's the lingua papillae. It's visible to the naked eye, so you don't need them to confuse you. They can ask you which taste is produced by amino acids as aspartic acid. If you remember what I mentioned here, let me go back. When I mentioned the 5 basic tastes, what did I say about the amino acid, glutamic acid and aspartic acid? They cause the umami taste. So when they ask you this question, you should know what you answer. Now, what if they ask you, what do pheromones stimulate? What does it stimulate? Hair cells, supporting cells, taste cells, olfactory cells, olfactory gland. Which one? I want you to write the question, what do pheromones stimulate? Put the answer for me in the comment section, all right? What about the primary olfactory cortex? Where is it located? Temporal lobe, right? I hope you don't forget that. What if they ask you, what is the only sense in which signals can reach the cerebral cortex without passing through the thalamus? I mentioned it. It's there looking at you. So I want you to comment on this video. Even if you don't want to comment, at least this one is something you know. Go down there right now. Put that question, all right? Put the answer for me. You know the answer. I'm not going to say it. Put it down in the comment section. You must comment, please. Now, let's talk about the hearing. Hearing is a response to vibrating molecules, all right? We know that. That's hearing. Equilibrium is the sense of motion, body orientation, and balance, all right? So both senses receptors reside in the inner ear. That is filled with fluid, all right, and sensory cells. Usually the fluid is set in motion and the sensory cells convert this motion into what? An informative pattern of what? Action potential. At the end of the day, it forms action potential, all right? And when you hear sound, it's usually any audible vibration of molecules. Anything can be vibrating. It can be air molecules, it can be objects moving, it can be anything that is pushing air, all right? And when you talk about pitch, you're talking about the sense of whether a sound is high or low. Loudness is the perception of sound energy, intensity, or amplitude of vibration. Extremely important that you know this as an introductory phase, all right? The hearing range is between 20 to 20,000 hertz. Extremely important that you know this, all right? And frequency determines what? Pitch. Frequency determines what? Pitch. Pitch is whether to know whether, how loud or low something is. And young people actually hears better at high frequency. That's why you see them playing a lot of loud stuff, you know? Not for old people like me. Okay, and when you start getting old, your hearing start decreasing, all right? The sensitivity start decreasing. How is sound detected? It's detected through mechanical vibration of air molecules. From there, it's converted to fluid waves in the cochlea. From there to stimulation of hair cells. From there to generation of electrical signals. And from there to natural transmission to auditory cortex. You need to know this sequence. You really need to know this sequence. Why? Because they give you questions a lot on it. For example, they may ask you, the human ear can detect what frequency of vibration. You already know 20 to 20,000 hertz. You already know that, all right? So later I will give you more questions, but I need to finish up this discussion before I give you more of this question. Now, anatomically, remember anatomically, we have the outer ear, the middle ear, and the inner ear. You need to know these structures. I don't want to say a lot of things. That's why I tabulated this way. The outer ear, the first one is the auricle, that's the pinna, is the visible part you can see. Then the auditory canal, the external acoustic meatus. Then it hits one membrane that locks out the outer ear. That membrane is known as what? Tympanic what? Membrane. After the tympanic membrane, if you just cross that barrier, you've entered the middle ear. Another name for the middle ear is tympanic what? Cavity. Tympanic what? Cavity. Now, there are three things you need to know about the tympanic cavity. One, it has 3 bone ossicles, all right? We call them Miss. Miss, how are you doing? Miss is for malleus, incus, and what? Stapes. So the incus is in between the malleus, is synapsing with the malleus, and synapsing with what? The stapes. You need to know this. Now, it also has, the middle ear also has the auditory tube, which we call the Gustation tube, and also the oval and round window. Oval, round window. So it has 3 bones, all right? It has a tube, then it has 2 windows. You need to remember this. Now, the inner ear structure, we have the semicircular duct, which helps for balancing. We have the cochlea, which helps for hearing. We have the vestibule, which helps for equilibrium. Chicken. This is what you need to know. VCS. Vestibule, equilibrium, cochlea, hearing, semicircular duct, balance. If they ask you in the exam, what takes care of balance? Semicircular duct. What takes care of hearing? Cochlea. What takes care of equilibrium? Vestibule. And if you look at this diagram very well, you'll be able to understand everything I just discussed, all right? The outer ear, the middle ear, and the inner ear. So take your time, look at the diagram, all right? You look at this diagram, you'll be able to understand very, very well what we are talking about. All right, so you can pause it, use it as your screensaver. Change his picture. Use this one as your screensaver, all right? Now, we want to discuss this sense of hearing with the most important things, all right? We've mentioned that cochlea is for what? For hearing. Cochlea is for what? For hearing. So let's dissect cochlea because it's the house of hearing. Thinking about the structure, it has what? Spiral-shaped snail-like structure like this, cochlea, all right? Spiral-shaped snail-like structure, if you look at it properly in this diagram, you see the snail-like structure? That is the cochlea, all right? Okay, now, it contains, that part contains what? 3 fluid chambers. The first one is the scala vestibuli, it contains the perilymph. The second one is what? The scala media. It contains what? The endolymph and the cochlear duct. So the cochlea has its duct inside it. That duct has what? Endolymph. Then it has the scala what? Tympani, which still contains what? Perilymph. So it means that the perilymph, you know, is gathered around, and in middle of it is what? The endolymph. And that endolymph is inside what? The cochlear duct. And that cochlear duct is so important in anatomy. Why? Because it is what houses the spiral organ of Corti. There's something called the spiral organ of Corti. Now, inside, if you keep going inside the cochlear duct, you see the spiral organ of Corti. Inside that spiral organ of Corti, there are components, very, very special components. 3 of them. We have the basilar membrane, we have the tectorial membrane, we have the hair cell. You need to know what they do. Each of them stands for. The basilar membrane of the spiral organ of Corti, which is contained in the cochlear duct, which is contained in the scala media, which is contained in the cochlea. You get the sequence. I want you to pause, slow down this video, then write it down and put arrows on it. All right. So that spiral organ component has the basilar membrane. The basilar membrane vibrates in response to. Once it vibrates, the tectorial membrane overlies the hair cells. We already know that. Now, what does the hair cell do? Immediately, the basilar membrane vibrates in response to sound. The hair cells is the actual sensory receptor. It's what detects that sound vibration. This is interesting, right? Okay, you know what? So let's discuss the inner ear properly. The inner ear cells, what do they do? We are gonna discuss the inner hair cells, the outer hair cells, and what's the stereocilia. The inner hair cells, the outer hair cells, and the stereocilia. These three things are called what? Mechanotransducer. Remember we talked about transduction. So now these things, they are converting these sound waves to what? To hearing or to action potential. Okay, the inner hair cells contains about 95% of cochlear nerve fibers, right? 95% is the inner hair cells. They are arranged in single row, and they convert mechanical vibration to what? Electrical what? Signals. So they act as transducers in the spiral organ. Extremely important that you know this. How about the outer hair cells, the ones at the outside? They're just amplifiers. They help to make it loud, to make it bigger. All right? They can contract and elongate, and they enhance sensitivity and frequency discrimination to know that, oh, this is music and this is loud noise. Oh, this is my name that they are calling, but this is somebody's name that they are calling. This outer hair cells. But the inner hair cells is the actual transducers, all right? And is the most numerous, 95%. Now we have the stereocilia, all right? They are hair-like projections on the hair cells, all right? The hair-like projections on the hair cells, they help to detect movement. Bending opens ion channels. Also, the upward movement opens potassium gates, all right? So that is stereocilia for you. Now you need to be consciously aware of the three bone ossicles, all right? Ossicles, like the meats. I mentioned it initially. The malleus, which is the hammer, the incus, which is the anvil, the stapes, which is the stirrup, all right? The malleus is attached to the tympanic membrane. It's the first bone in the chain. So this is the malleus attached to the tympanic membrane. Then the front is attached to what? The incus. The incus is attached to both the malleus by this direction and also the stapes by this direction. So the incus is the middle bone of the chain. Very, very important. So it articulates with both malleus and stape. Now it forms the synovial joints on both ends, all right? Why the stapes, which is the styrus, is the smallest bone in the human body. They will ask you, which bone is the smallest bone in the human body? It is the stirrup, that is the stapes. Anyone they give you the names, you should be able to pinpoint it, all right? And it helps to transmit vibrations to the inner ear. So the idea of these bone ossicles is just to amplify sound vibration, all right? Make sounds, as much as 20-fold. Very, very important. So if you want to go from, the complete sound transmission pathway from out to in, you understand? When sound wave passes the pinna, they enter the auditory canal, all right? So it travels through the auditory canal inward. Then it hits the tympanic membrane. When it gets to the tympanic membrane, it vibrates it, all right? Now, in response, the ear or that vibration enters the middle ear, right? Where you jam the ear ossicles, that's the miss. Now, the ear ossicles does what? Amplify the vibration. And when they amplify the vibration, when they amplify the vibration, what happens? The vibration moves through the oval window and transfers the fluid, right, into the inner ear. Now, in the inner ear, where you meet the cochlear duct, you understand, the fluid, generates wave. That wave it generates stimulates the spiral organ, all right? It stimulates the spiral organ, the hair cells in the spiral organ. Those hair cells in the spiral organ are what initiates what? The signals that goes to the brain, because they are the fibers which we call the cochlear nerve. Very, very important for you to understand this. So the critical point for all this is sound must be converted from air vibration, fluid wave, you understand, so that it can stimulate what? Hair cells to create what we call what? Electricity or action potential that goes to the brain. So you see, this movement, even the little sound is amplified, all right? So this sequential amplification ensures weak air vibrations can stimulate inner ear receptors. Extremely important. So you have to memorize that the canal, membrane, ossicles, window, duct, organ, nerve, all right? Canal, membrane, that's the tympanic membrane, ear ossicles, the oval window, the duct, the organ, and what? The nerve. That's the sequence. Extremely important that you know this. Now, this is the projection pathway. Let's understand the projection pathway properly. All right? Looking down left, you will see the cochlea. Extremely important. You see the cochlea. So sensory fibers begin at the base of the hair cells. That's what you need to know. Sensory fibers begin at the base of the what? the hair cell. Now, immediately the axons lead away from the cochlear nerve. So if you look at that red thing, you see the arrow moving inwards to the yellow circle, all right? That's the cochlear nerve from the cochlea moving inwards, all right? Where is it going to? To the brainstem. Very, very important that you know this. So as it's moving inwards, it's joined with the vestibular nerve to form what? The vestibulocochlear nerve, which is cranial nerve 8. So the ear sends nerve fibers to both sides of the pons. And that is what you are seeing there, cochlear nucleus of the pons, all right? That's where it ends. Now, there's a synapse there, right? With the second order neurons. The second order neuron starts going up. It ascends to nearby superior olivary nucleus. This is the superior olivary nucleus, the one on light blue. Superior olivary nucleus of the pons. So this superior olivary nucleus issues something we call efferent fibers back to the cochlea to tune the cochlea. So if you look at it very well, it issues it back. We call it cochlear tuning. And apart from that, the superior olivary nucleus also helps in binaural hearing. When we talk about binaural hearing, we are trying to compare, like that is when the ear is comparing signals from both the left and the right ears, all right, to be able to identify the direction from which a sound is coming, all right? That's what you see down there, where you see the cranial nerves 3 and 7 coming downward. Very, very important. Now, other fibers are sent to the inferior colliculus of the midbrain. All right. The idea of this inferior colliculus of the midbrain ascension is to help to locate the origin of the sound. You understand? And also to process fluctuation in pitch and mediate the startle response and rapid head turning in response to what? Loud noise. Extremely important. So from there, the third order neuron begins in the inferior olivary colliculi, you understand, and goes up, straight up towards the thalamus. Extremely important. Then from the thalamus, the fourth order neurons from the thalamus, they go to where? The primary auditory cortex, the superior margin of the temporal lobe. And the idea is for conscious perception of what? Of sound. Extremely important. So there's extensive decusation. And the idea of this extensive decusation is so that damage to one side of the cortex does not cause unilateral hearing loss. Very, very important. All right. So it's very, very diversified. All right. So if you look at this diagram also, you see the vestibulocochlear nerve, the two of them, they move up to the pons. From the pons, they move to the inferior olivary colliculus of the midbrain. From there, the third order neuron synapse the thalamus. You understand? Then the fourth order neuron carries it to the brainstem. Very, very straightforward. That's the red arrow moving up. Now let's talk about protecting your hearing. But before we talk about protecting your hearing, I need you to know about the two types of deafness. All right, deafness is called hearing loss. All right, the two types, we have the conductive deafness and also we have the sensorineural deafness. When we are talking about conductive, all right, it talks about transmission of vibrations to the inner ear. When it is interrupted, that transmission is interrupted, that's conductive. So outer and middle ear problem leads towards conductive hearing loss. All right, so usually as a result of damage. Now let's talk about deafness. All right, before we talk about protecting your hearing. So deafness is known as hearing loss, all right? There are two types. We have the conductive and we have the sensorineural. When you're talking about conductive, that's conduction, all right? How it transfers, how it moves, how vibration moves from the outer ear to the inner ear, all right? So the damage is usually the outer and also the middle ear. So we talk about damage to the tympanic membrane, otitis media, all right? Blockage of auditory canal, osteosclerosis, stuff like that. All right, can interrupt the movement of vibration from the outer to the inner ear. That's conductive. When you're talking about sensorineural, that is what? Nerve deafness. Nerve. All right, so death of hair cells. Remember, hair cells generate that action potential that transfers into the nerves. So those death of hair cells, all right, maybe, some factory workers, musicians, construction workers, they usually have this sensorineural deafness. So sensorineural is talking about what? Inner ear problem. Inner ear problem, hair cells problem. All right. Now, talking about how do we protect your hearing, they will ask you a question: which part of the ear is most vulnerable to irreversible damage? That is what? Cochlear hair cells. So you must protect it by all means. All right. Why? Because it cannot regenerate in mammals. It can't. It can damage as a result of loud noise. That's what we call mechanical damage. All right. Or sometimes those loud noise, when it's continue accumulating, it can damage somebody's cochlear hair cells, over time. The ones that are less vulnerable to damage is things like ossicles. They rarely damage. Tympanic membrane, even if it damages, it can heal, all right? Tectorial membrane is protected by the bone. Cochlear nerve axons, all right? They are very, very resilient. So it's you need to know which ones are less vulnerable and which ones are what most vulnerable. So most vulnerable, cochlear hair cells. So you need to just limit, how you expose yourself to sound greater than 85 decibels, all right? Also use hearing protection, especially if you're in a loud environment, all right? And take breaks from loud environments. These ways you can protect your hearing. When you're talking about tonotopic organization, you're talking about how do we detect pitch, all right? How do we know, oh, this is high pitched, this is low pitched? There's something we call the basilar membrane, all right? So pitch depends on which part of the basilar membrane vibrates, all right? The basilar membrane has two parts, the basal end and also the distal end. And one thing you need to know is that, the basal end membrane is usually narrow and stiff, while the distal end membrane is 5 times wider and more flexible, all right? 5 times wider, more flexible. And the brain interprets signals that happen on the distal end as what low pitched, while signals that happen on the basal end as high pitched. That is just it. And how does the stereocilium of the inner ear hair cells function? How? We call it mechanotransduction process. That's ion channel activation in hair cells. Extremely important that you know this. All right. So usually there's something we call stereocilia. All right. The stereocilia, they stand beside each other, all right? Now, they have a stretchy protein filament. We call them tip link. You understand? So this stretchy protein filament, the tip link, connects ion channel of one stereocilium to the next stereocilium. So the ion channels is connected. And as they are connected, the tallest stereocilium is bent, when the basilar membrane rises up toward the tectorial membrane. Extremely important that you know this, all right? You can pause this and listen to it again. Now, it pulls on the tip links and opens the ion channel. Once it opens the ion channel, what happens? Potassium flows in. That potassium flowing in leads to depolarization, which causes the release of what? Neurotransmitter. Extremely important that you know this. Usually glutamate, all right? So this neurotransmitter release stimulates the sensory dendrites and generates what? Action potential in the cochlear nerve. So this is how it works. This is how the cochlear nerve fibers are activated. Extremely important. So it's usually the stereocilium, all right? This one bends over, you understand? The tip link connects the ion channels, immediately connects the ion channels, the channels open up, all right? Potassium cation flows in. When it flows in, it causes what? Depolarization, because the cell becomes more positive, causes depolarization. And that depolarization will release what? Neurotransmitter, which stimulates what? Cochlear nerve. I hope you understand this because I have to explain it 2 times. Now, going back to the beginning, all right, I failed to mention to discuss more the auditory tube. That's the Gustation tube. It's just a structure, right, that connects the middle ear to the nasopharynx. That's the truth, all right? Extremely important. It usually collapses but opens during swallowing, yawning. When you yawn, it opens up. What's the function? It helps to equalize pressure between the middle ear and what? The atmosphere. Very, very important. That's why sometimes it's as if your ear is locked up, all right, or air entered your ear too much. You understand? Because the Gustation tube is trying to, allow pressure equalization, especially during altitude changes, like when you in flight. What is the clinical significance of this? Upper respiratory tract infections, right, spread into the ear, leading to what? Otitis media. That's what usually causes middle ear infection in children, especially. And this is why when you are cold, it always leads to ear infection, many times. So as a recap, let me ask you some questions. Which structure acts as a transducer in the spiral organs? Stereocilium, inner hair cells, tectorial membrane, round window, basilar membrane. What is your answer? Inner cells. You can't forget this. Okay, let me ask you another question. The spiral organ is housed within which of the following structures? Scalar vestibular, scalar tympani, cochlear duct, anterior semicircular duct, vestibule. I want you to pause, answer this question, or put the answer in the comment section. All right? The answer is what? Cochlear duct. So the spiral organ is housed in where? The cochlear duct. I mentioned it when we were discussing. What if they ask you about which structure allows the upper respiratory infections to spread from the throat to the tympanic cavity? That is the auditory tube, or what? The Gustation what? Tube. So you have to remember that. And they want to convince you with tympanic cavity, auditory canal, cochlear duct, oval window. Please, it is auditory tube. Extremely important that you can remember this. Now, what if they ask you the direction, all right, how stimuli is being produced? Remember, it is from the auditory canal to the tympanic membrane, to the ear ossicles, to the oval window, to the cochlear duct, to the spiral organ, to the fibers of where? The cochlear nerve. And remember that cochlear hair cells are the most vulnerable to irreversible damage caused by what? Loud noise. Cochlear hair cells. And each upward movement of the basilar membrane causes the stereocilia of the inner hair cells to bend, opening what? Potassium gate, not sodium, not calcium, not chloride, not magnesium, but what? Potassium gate. When you talk about equilibrium is coordination, balance, orientation in three-dimensional space, all right? Yeah. So we talk more about the vestibular apparatus, because the vestibular apparatus is what is in charge of equilibrium, all right? This vestibular apparatus has two major things. One is the semicircular ducts, all right, which is focused on angular acceleration or rotational acceleration. And the other one is the two chambers, which is the sacule and the utricle. Sacule is anterior, utricle is what? Posterior. And both of them are responsible for static equilibrium and for linear acceleration. So the question is, how do they work? Now, the semicircular canal, right? It's a three fluid loops, right? Positioned at right angles to each other. So we have the anterior, the posterior, and the lateral canals, all right? Just like a compass, positioned like this, the three of them, all right? So each canal contains a widened base. That base is known as what? Ampulla or ampullaris, crista ampullaris. Now, this ampulla houses actually the crista ampullaris, yes, which is a sensory crest stopped. So there's these hair cells that are embedded in a gelatinous scapula, all right? They are just there. So when you rotate your head like this, all right, the inertia of that endolymph bends that scapula. And when that scapula is bent, it deflects the hair cells. And that deflection signals rotational acceleration in any plane. So it's just like you saying yes, 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 or no, 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 no. You understand? Or do your head like this. This is exactly what happened. That is exactly how semicircular canal helps to identify rotational movement. It's just a rotational movement detector. It's as simple as that, all right? So I briefly listed out everything you need to know about the rotational movement. That's the dynamic equilibrium, all right? The three semicircular ducts or canals, all right? The mechanism, the crista ampullaris, the cupula, that's the gelatinous scalp, where the hair cells is embedded, right? Then the endolymph, which is the fluid, right? That bends the cupula, you understand? Leading to that angular detection. Very, very important that you understand this. Now, when you talk about static equilibrium, right, you are talking about the otolytic organs. What are the otolytic organs? The utricle and the sacule. Do you understand? They are in charge of linear movement and gravity detectors, all right? The utricle and the sacule, right, are membranous sacs containing macula, all right? So that macula is just patches of hair cells, right? On top of it, it's crowned with something like that looks like a gelatinous layer. Now, that gelatinous layer, there are stones on it. We call them ear stones or otolites. They are ear stones or otolites. They are carbonate crystals. So when there is gravity, all right, or when there is linear acceleration, these dense crystals, they shift. When immediately they shift, what do? Those stones, they shift, and immediately they shift, they bend the hair cells to signal your head's position relative to gravity and detect both forward movement, backward movement, up and down movement. You understand? Like when you are riding an elevator or when you are accelerating in a car. So, in summary, elevator movement, that's linear vertical, right, is detected by hair cells of what? The macula saculi. The macula saculi, all right? And this is as a result of that stone movement. That's otolytic membrane movement with gravity. But when you are spinning in a swivel chair, right, angular movement is detected by what? Semicircular duct. And it works with what? Endolymph, which causes that lagging when your head bends. Very, very important that you understand this. Also, the bending of the capula in the crista ampullaris also causes the endolymph to lag. All right? So all these things leads to you sensing that you are moving around. That is angular movements. So just know that angular movement is semicircular duct, and know that what? Linear movement is what? Macula saculi. Now, when we are talking about car acceleration, straightforward movement, car acceleration, all right? That is what macular utriculi. That's the utricle. The utricle. Car acceleration. But when you are moving up the elevator, that is what macular circuli. And when you are speeding round, that is what semicircular duct. Chicken. If you understand this like this, you are good to go. Now, after this, what happens? When the sound has been detected, it moves into the nerves. First of all, the vestibular nerve. The vestibular nerve conducts from the utricle, the sacral, the semicircular duct. Then it merges with the cochlear nerve for hearing. Remember that. So both of them forms what? The cranial nerve, what? 8, which is vestibulocochlear nerve. So the vestibular nerve is more about positioning, while the cochlear nerve is more about hearing. Then from there, they move to the vestibular nuclei in the brainstem, medulla, and the pons. From there, they relay the information to the relay station, which is the thalamus. Then the thalamus disperses it to the cerebral cortex. That is conscious perception of balance. Very important that you understand this. So this is the movement. This is as we've described it. All right. The vestibulocochlear nerve from the vestibular apparatus. All right. They move straight to the pons. From there, they move to the thalamus. Then from the thalamus, they move to the cortex. Sometimes they can ask you questions like, when you travel in an elevator, what sense is when the elevator is moving, right? You should be able to bear in mind that the hair cells of the otolytic membrane or the macular circuli is what detects this elevator movement. I've already described it. So I need you to go back to this video. Just go take it back a little, understand it properly. They can also ask you about the crista ampullaris. What is it associated with? Remember that crista ampullaris is associated with the dynamic equilibrium in angular what? Movement. Dynamic equilibrium in angular movements. That's the crista ampullaris. All right. And sometimes they can give you a list of things and ask you which of the following does not contribute to the sense of equilibrium. So you should know which ones contribute to the sense of equilibrium. Things like the otolytic membrane, semicircular canal, the sacral, the utricle. All right. Extremely important. All of them are vestibular apparatus. Now let's go to vision. All right. Vision is the perception of objects in the environment by means of lights that they emit or reflect. Correct? Yes. You need to understand this. All right. And human eyes, the wavelength of light, you can see is 400 to 700 nanometer. All right. And light must cause a photochemical reaction to produce what? A nerve signal. So now we want to convert light towards electricity. Very, very important. And it is very good for you to know that, for light detection, photoreceptors in the retina respond to photons, right? The rods dim light, the cones color. We are going to discuss this more as we continue in this discourse. All right. You should also know some facts that 70% of the sensory receptors in the body are in the eyes. For real. Visual cortex comprises about more than 30% of cerebral cortex. So that's how dominant the eyes is. It's extremely dominant. And you need to understand it. Looking at the eyes, you see the main component of the eyes. You see the cornea, right? Other things in the cornea like the pupils and others, the lens. Those are the main components of the eyes. But we have accessory components like the conjunctiva. It's an accessory component. The palpebra, as you're looking at it, the muscles, the extraocular muscles, the superior obliques, the lacrimal apparatus, all these things are what? True accessory structures of the eye, but cornea is actually a main structure. It's part of the eyes itself. You understand? It's just this transparent. If you look at it there, it's just a transparent, anterior portion of the eyeball, which is continuous with the sclera, and it helps to bend light. It reflects light. Extremely important. Also, before I continue, I also want to talk about the extrinsic muscles of the eyes. If you look at it very well, you see the different extrinsic muscles. There are about 6 of them. We have the superior, the inferior, the lateral, the medial rectus muscles. We have the superior and inferior oblique muscles. These are the 6, external muscles of the eye, extrinsic muscles of the eyes. All right. And you need to know their cranial innervation. I keep telling you the formula. If you look at my video, the other video in the Neuro 1, Neuro 2, Neuro 3, if you've not looked at it, please go check it. I keep referring you to it because when you understand it more, you'll be able to understand this concept. All right. Formula LR6 SO4 A3, lateral rectus cranial nerve 6, superior oblique cranial nerve 4, and all others are cranial nerve what? 3. Extremely important that you know this formula, all right? Because superior, inferior, medial, and lateral rectus, they move the eyes up, down, medial, and laterally, respectively, all right? While the superior and inferior oblique turn the 12 o'clock pole of each eye toward or away from the nose, something like this, away from the nose. They also produce slight elevations and depressions of the eye. These are very important and crucial information you need to know about these extrinsic muscles. So if you look very well, you see the optical components of the eyes, transparent elements that admit light, reflect light rays, and focus the images on the retina. like the cornea, the aqueous humor, the lens, the vitreous, the vitreous humor. All these things helps to control the eyes. And after the cornea is transparent anterior cover, all right? While the aqueous humor is serous fluid that is secreted by what? The ciliary body secretes what? That serous fluid known as what? The aqueous humor, all right? And it secretes it into the posterior chamber. That's posterior to the cornea and anterior to what? The lens. And it's reabsorbed by what? The sclera venous sinus. The sclera venous. There's a reason why I'm mentioning this, because it has serious clinical significance, all right? So production is ciliary body. Reabsorption is by the sclera venous what? Sinus back into the blood. Then we talk about the lens, all right? The lens, very, very important, suspended by the suspensory ligament, all right? It has fibers which pull it, all right? Then we talk about the vitreous body, which fills the vitreous what? Chamber. The chamber between the lens and the retina. That's the chamber behind the lens, all right? Extremely important that you know this. The one in front is the aqueous. The one behind the lens is what? The vitreous. So we use the lens as a separator. And you should also know about the glaucoma, because they call it the silent thief of sight. Very silent. And it's always as a result of elevated pressure within the eye due to obstruction of the sclera venous sinus and improper drainage of what? The aqueous humor. I told you the sclera venous sinus drains. So when we block the drainer and, it keeps producing, before you know it, it will raise the ocular pressure, right? To raise the ocular pressure because of the obstruction of the sclera venous sinus, remember? Preventing drainage of aqueous humor, you understand? Pressure builds up and leads to what? Damages of the optic nerve, you understand? And also progressive peripheral vision loss, which can lead to blindness if untreated. How do we treat it? We can increase the drainage. We can just open up the drainage, or use laser surgery, or we can even use eye drops to reduce what? Fluid production. Chicken, you are good to go. So if we allow that pressure to build up, it will compress those retinal cells, and the retinal cells, when they are compressed, they lose oxygen, and when they lose oxygen, problem. And when the vision is lost, it cannot be restored. All right? So that's glaucoma. Another one we can compare it with is the cataract. Cataract is just clouding of the lens. You see, that lens we are talking about, when it clouds, that is cataract. Can be caused by diabetes, smoking, UV rays, drugs, or viruses. How can we treat it? By replacing the natural lens with plastic one. Simple. All right? So if you look at the appearance, microscopically, you'll be seeing clefts, you've seen debris, you'll be seeing bubbles. Extremely important that you understand. The neural components of the eye includes the retina and the optic nerve, all right? We need to know about the retina and the optic nerve. So dissecting the parts of the retina, there are 3 major parts you should know, especially when you use the ophthalmoscope to check. When you examine the retina with the ophthalmoscope, you're most likely going to see the macula lata and also the fovea centralis. The macula lata is the patch of cells on visual axis of the eye, while the fovea centralis is the pit in the center of what? The macula lata, all right? Usually where you see the blood vessels of the retina. Extremely important. So in the fovea centralis, there's no rods in fovea at all. That's where you have the sharpest vision and the highest concentration of what? The cones. While in the macula lata is just also for high concentration of cones, yes, all right, specialized for high acuity tests. Extremely important. We call it the yellow spots. But the part where, you need to understand more is the optic disc. Optic disc. The retina is attached to the eye only at what? The optic disc and also the ora serrata. But the optic disc is important because it's the posterior exit of the optic nerve. Extremely important that you know this. It's the posterior exit of the what? The optic nerve. And it contains no photoreceptors. That's what we call physiological blind spot. Finally, you need to know that the retina is formed from the optic vesicles, which are the outgrowth of what? The diencephalon, if you watch the other video. Different distances your eye adjusts to view objects, all right? That is what we call what? Accommodation. Accommodation is focusing different what? Distances. And this is done by the changes in lens curvature. Lens curvature. What's the mechanism for close range vision? Contraction of the ciliary muscles. When ciliary muscles contract, it leads to changes in the lens curvature, right? The lens becomes more convex. And at that moment, the depth of focus, widens as a result of constriction of the pupil, all right? Widens as a result of constriction of the pupil. And also the extrinsic muscle, eye muscle, right? They converge. See, all these things helps for accommodation. If it's a ciliary, that's for close range vision. If it's for distant vision, ciliary muscles what? Relax. Remember, close range, we say ciliary muscles what? Contract. But this time around, ciliary muscles relax. For close range, the lens changes curvature, right? Becomes round or convex. But for distance, the lens flattens out. Extremely important that you understand this. Now, you need to know that there's something we call normal vision, which is a metropia, all right? No corrective lens is needed. Image is focused directly on the retina, all right? So based on focusing of image on the retina, that's which is normal. If the image is not focused on the retina, it becomes what? Pathology. Example is myopia, all right? For myopia, usually when the eyeball is too long or too large, all right? Or the lens is too strong. So what happens? The image is now focused what? In front of the retina. So because of that, you are able to see near objects very well, but you can't see far objects properly. That is called what? Myopia, or what? Nearsightedness. And we can correct it with what? Concave lens. Another one is hyperopia, which is farsightedness. This one, the eyeball is too small. The image is formed behind the retina. And because of that, near objects become blurry, but far objects becomes what? Very clear. This is corrected by what? Convex lens. So you need to know the problem and you need to know the treatment. So in summary, near response is usually adjustment of close range vision, which requires convergence of eyes, constriction of pupil, and accommodation. Extremely important that you know this, all right? Emetropia is what? Normal. Also, we have presbyopia, all right? This is usually age-related when you're getting old, all right? Usually after the age of 40. You understand? The lens becomes less elastic, all right? So you need glasses to start reading properly. Then we have astigmatism. Virtually everybody has astigmatism. Astigmatism is usually as a result of irregular curvature of the cornea or the lens, all right? So it causes blurring, especially of the distorted vision at all distance, whether near or far. We correct it, astigmatism, using what? Cylindrical lenses. Extremely important that you know this. Now, the retina has the pigments, that's rhodopsin, which absorbs stray light to, so visual image is not degraded. It helps to make image clearer, but it doesn't form image, all right? So we have the neural components of the retina, which are the photoreceptors, the bipolar cells, and the ganglion cells. The only one that form images, usually what? Only the rods and the cones produce what? Visual images. And the rods and the cones are examples of what? Photoreceptors that absorb light and generate a chemical or electrical what? Signal. Very important. But we have the bipolar cells, all right? The bipolar cells are the first order neurons. They have dendrites that synapse with rods and cones, and axons that synapse with what? Ganglion cells, all right? So the ganglion cells are the second order neurons. They are the largest neurons in the retina and are arranged in a single layer next to the vitreous body. So you need to understand this. Now, when we talk about the rods specifically, all right, the rods detect what? Dim lights or night vision. We call it scotopic, dim light or night vision. Scotopic what? Vision. So black and white, no color. Black and white, no color. But when you are talking about color, you are talking about what? Cone, all right? They are actually shaped like cones. They contain photopsin pigments, all right? The other one is rhodopsin. This is photopsin pigments. The function, lower sensitivity than rods, high resolution, fine detail, color vision. That color vision, we call it what? Trichromatic. Trichromatic. While the rods, the dim light, we call it, or the dark vision, we call it what? Scotopic. Trichromatic. Color for cones. Trichromatic. Color for cones. Look at this question. What is the correct order of cells in the retina from back to front? From back to front. That's when you are talking about the photoreceptor, the bipolar, and the ganglion. I just mentioned it not too long ago. Yes, not too long ago. When I was telling you the neural components of the retina, I mentioned the photoreceptors, the bipolar cells, and the ganglion cells. Photoreceptors, the bipolar cells, and the ganglion cells. This is the order. So the bipolar cells is bipolar because it's facing the ganglion, all right? And also it's facing what? The photoreceptors. Extremely important that you know this. So as a recap, remember what glaucoma is, all right? It's when usually involving the scleral venous sinus blockage. Extremely important that you know this. Also, they may ask you a question, axons from all regions of the retina converge on the, where do axons of all retina converge? That is optic disc. I mentioned it initially. And also know about accommodation. Usually, accommodation, when you view objects close to the eye makes adjustments. Like I bring something, the eye makes adjustment to be able to see it. I take it far, the eye adjusts to be able to see it. That is what accommodation. That is what accommodation. You need to know the difference between accommodation and emetropia. Emetropia is normal eyes. It does not need any corrective what? Lenses. Emetropia, accommodation. So they may ask you which cells are responsible for photopic vision, that's day vision, or trichromatic color, cone. And sometimes they may ask you, why do cones exhibit less neural convergence than rods. And the reason is because of the photopic vision has what? Higher resolution than scotopic what? Vision. Color vision has higher resolution. I mentioned this thing initially. Has higher resolution than what? Scotopic what? Vision. And because of that, it does not need so much what? Neural what? Convergence. Now let's talk about retinal signal processing. We have the first order neurons, the rods and the cones. They detect lights. They use graded potentials. No action potential here. Just graded potentials. All right, that's local, local potentials, they're graded. Now, second order neurons, they're usually the bipolar cells. They transmit signals from where? From the photoreceptors to where? To the ganglion. Remember I told you photoreceptor, ganglion. Photoreceptor, ganglion. All right, so the third order neurons are the what? The ganglion cells. And you should know that the ganglion cells are the only retinal cells that produce what? Action potential. They will ask you, what are the only retinal cells that produce action potential? That is what? Ganglion cell. Ganglion cell. Now, the duplicity theory, all right? Why two receptors are always needed? You cannot have only one receptor. Why? Because a single type of receptor system cannot produce both high sensitivity and high resolution. It's either producing high sensitivity or producing high resolution. Either or. All right? So, for example, the rod system, the scotopic vision, high convergence, high sensitivity, low resolution. That's poor detail. The cone, photopic, low convergence, high resolution, all right, low sensitivity. So they will ask you, describe the duplicity theory of vision. A single type of receptor system cannot produce both high sensitivity and high resolution at the same time. Know that, no peace. So if they ask you the first order neurons, you should know that it's bipolar, all right? You should know it's bipolar. I mentioned it initially. Initially I mentioned the retinal signal processing. Bipolar are the second order neurons. But in the visual pathway, please, if they ask you a question on the visual pathway, the bipolar are the first order neurons. In the retinal signal processing, they are the second order neurons. But in the visual pathway, they are what? The first order neurons. So let's discuss the visual pathway, projection pathway properly. Looking at this diagram, first of all, you need to know that the bipolar cells of the retina are the first order neurons. First order neurons. They will ask you that in exam. All right? They usually do ask that question in NCLEX. So the retinal ganglion cells, the second order neuron. All right? Retinal ganglion cells, the second order neurons, whose axons form what? Optic nerve. The axons form what? Optic nerve. So the optic nerves, if you look at it very well, you see the optic nerve going inwards from the eyes. The optic nerves, they combine to form what? The optic chiasma. That is the optic chiasma in the middle there. The optic chiasma. So half of the fibers in the optic chiasma cross over, just half. So half from this guy, half from this guy. Half of this from this guy moves over here. Half of this guy moves over here. Then some still continues on the same path. The other half continues on the same path. This is what we call what? Hemidecusation. Hemidecusation. And when this happens, the chiasma or the chiasm splits to form what? Optic tract. Optic tract. So from the optic chiasm towards the optic tract. So that's because of this. That's why the right cerebral hemisphere sees objects in the left visual field, because their images fall on the right side of each retina. And also each side of the brain sees what is on the side where it has what? Motor control over the limbs. It's very, very important that you understand this. I need you to pause this thing, listen to it again, and understand it. All right? Bipolar cells, first order neuron, ganglion cells, second order neuron, they form the optic nerve. Optic nerve combines to form the chiasma. The chiasma splits into to form to what? The tract. Now, how does the tract move? If you look at it very well, you see the tract. How does it move? See, when the tract comes down, one goes up, all right? So the optic tracts, they pass laterally around the hypothalamus. They circumvent the hypothalamus like this. You understand? Most of the axons now ends in the lateral geniculate nucleus of where? The thalamus. They always stop at the thalamus. From there, the third order neurons arise from that thalamus and form the what? Optic radiation of fibers in the white matter of the cerebrum. Very, very important that you know this. Then from there, they project to the primary visual cortex of the occipital lobe, where conscious visual sensation occurs. Now, some of it, if you look at this very well, you see that some of the optic nerve fibers, they project to the midbrain and terminate in the superior colliculi and the pretectal nuclei, all right? These are just the ones that controls visual reflexes of the extrinsic muscles of the eyes. Extremely important that you know this. And also, they are usually involved in pupillary and the accommodation reflexes, all right? So very, very important that you know this. So the ones that go to the primary visual cortex are not the ones that helps in all those reflexes. Instead, the ones that go to the superior colliculi and the protectile nuclei, the ones that helps in reflexes. But the one that goes to the primary visual center is specifically for what? Visual sensation. Extremely important that you know this. So that is the visual pathway. So that is the formula I mentioned initially. LR6, SO4, O3. You know what it controls. So, you look at it, your leisure. I've already discussed this before. Then this is light adaptation, and dark adaptation. Light adaptation is very fast. Dark adaptation is very slow, right? When you are in dark environments and suddenly there's light, it's so fast for you to adapt because your pupils constrict, reducing light entry. Then immediately the rod sensitivity decreases, cone activity increases, and rhodopsin bleaches. It's very, very rapid. You understand? Like when you step outside to the sunlight, or when they put on the light, you adjust very fast. But in darkness, it takes you time to adjust when you move from bright light to dark place, right? It takes very little time, right? Because the pupil dilates. When pupil dilates, it increases the light that is entering the eyes, all right? Then the rod sensitivity increases, the rhodopsin regenerates, the cones becomes less active. So it's very slow, 20 to 30 minutes before you are able to master your environment in a dark place. All right, that's if you even end up mastering it. But light adaptation is extremely rapid. So they may ask you questions like, half of the axons of each optic nerve decussate at the, look at it, it decussates at the, decussates the optic what? Chiasm. Optic what? Chiasm. You can't forget this. And also adjustment to close range vision involves all of the following. What the things that are involved in adjustment of close range vision? Acuity, extrinsic eye muscles, yes. Change in the curvature of the lens, yes. Constriction of the pupils, yes. Ciliary muscle activity, yes. All these things are involved. So they may ask you which one is not involved. Anyone that is not part of these ones, you rule it out. We've already discussed this. So going back to the vestibular, they can ask you the correct order, all right, for the vestibular projection pathway to the brain. How? What is the order? So you remember it's from the vestibular nerve, from the vestibulocochlear nerve, then to the vestibular nuclei, then to the thalamus, then to the what? To the cerebral cortex. I should mention it again so that you'll be clear. Vestibular nerve, arrow, vestibulocochlear nerve, arrow, vestibular nuclei, arrow, thalamus, arrow, cerebral cortex. That's how you need to know it. All right. So this is more like a recap. So we discussed a lot of questions today, more than 50 questions. I need you to take pen and paper and look at those questions. All right. Write them down, understand them very well. All right. This is a summary of everything we've done. All sensory receptors output electrical energy, receptor potential. Thalamus is the relay center, except in olfaction. Cochlear hair cells are most vulnerable to noise damage. Brain has no pain receptors. Convergence determines sensitivity versus resolution trade-off. Duplicity theory, we already discussed it. One receptor cannot have both high sensitivity and high resolution. And also we talked about the accommodation, what it involves. That is the ciliary muscles, right? And not light adaptation. We also talked about only ganglion cells produce what? Action potentials in the retina. Half of the optic nerve fibers cross the optic what? Chiasm. So you need to understand this, all right? And thank you so much for listening. I hope you appreciate this. Please give me a like. Please try to subscribe. Please try to make a comment. These things are very important to me. If you finish watching this video, I want you to write ready at the ending. That's the motto. Any of my videos you watch, please put ready. Please subscribe to this channel. Thank you so much and have a nice day.